Now we switch to frequency analysis of discrete time LTI systems. So we're going to start from the definition of frequency response. Discrete time LTI system can often be described using difference equation. And if we take discrete time Fourier transform on both sides of the equation, we can get a new expression in the frequency domain. Now, if we define the frequency response as the ratio of the zero-state response and the input signal in the frequency domain, then we can get this fraction. And this fraction is determined by the coefficients in the difference equation. And what is the relationship between the frequency response and the system's impulse response? Now let's take a look at this system. By definition, it's the ratio of the zero-state response and the input. And now if we force the input equal to delta k, then the zero-state response is equal to the system's impulse response. So it is clear that the system's frequency response and the system's impulse response are a pair of discrete time Fourier transform. We may also provide another view angle to look at the system's frequency response. Now we input an imaginary exponential signal into a discrete time LTI system. Then the zero-state response of the system can be specified by this convolution. Now we plug in the definition of the convolution. And if you move this part outside summation, you get this new equation. If you look closely this inside the summation, you will realize that this actually is the discrete time Fourier transform. So graphically, we can represent if this is the input, then the output is the same imaginary exponential signal multiplied by the system's frequency response. So here is the explanation. So when you have imaginary exponential signal, the response to that signal will be the same imaginary exponential signal, but modified by the system's frequency response. In other words, the system's frequency response actually is the transmission property to different frequency components. In general, this frequency response is a complex function, so it has two components. The amplitude part is called amplitude response, while this part is the system's phase response. And in case that the system's impulse response is a real function, then we're going to have a conjugate symmetry in the frequency response. Or in other words, the amplitude response is even while the phase response is odd. In case that we input a sinusoidal signal, for example here is a cosine function, into a discrete time LTI system, due to Euler equation, we can break the cosine function into two terms. Each of them is an imaginary exponential signal. So based on the understanding, the zero response of the system actually is the sum of the response of these two imaginary exponential signals. Then, based on the conjugate symmetry property, we can further simplify this expression into another cosine function. with the same frequency, but the amplitude will be modified by the system's amplitude response, and the phase is modified by the system's phase response. Similarly, we can get the conclusion for sine function. So the discrete time LTI system responds to a sinusoidal signal is another sinusoidal signal with the same frequency, but the amplitude and phase both will be modified by the system's amplitude response and phase response respectively. Now let's take a look at one example in here. We have a DC LTI system whose frequency response is depicted in this plot. And we're asking what is the response of the system to this input. We learned already a discrete time LTI system's response to a cosine function is another cosine function, but modified. The input actually has 4 cosine functions summed up. So each of them will have to follow this rule. When the frequency is equal to 0, then the amplitude response is equal to 1. When the frequency is equal to 0.5 pi, the amplitude is equal to 1 as well. If the frequency changes to 0.75, the amplitude is 0.5. When the frequency is equal to pi, then the amplitude is equal to 0. So that the response to x of k actually is the summation of the 4 responses there. What if we change the discrete time LTI system? The amplitude is the same, but we have an extra phase response. Similar idea can be applied. So the cosine function will cause another cosine function, but modified by the amplitude response and the phase response. So these are the response to the specific frequency components. And these are the phase response to the specific frequency components. And we just sum them up to get the zero state response of the system to this input signal. Now let's summarize the definition of the frequency response for a discrete time LTI system is defined by the ratio of the zero state response and the input in the frequency domain. Or in other words, it can be defined as the discrete time Fourier transform of the system's impulse response. The concept of the frequency response can be treated as the response of the system to an imaginary exponential signal. The response is the same imaginary exponential signal, but modified by the system's frequency response. So the frequency response actually is the description of the system's transmission property for different frequency components. And that frequency response has 2 parts. One is the amplitude response. The other is the phase response. Thank you.